Right now, 2 spacecraft are flying through interstellar space. They left Earth in 1977. They were designed to last 5 years. Nearly 50 years later, they are still running. And we have sent nothing to follow them. Voyager 1 is over 15 billion miles away. A signal from Earth takes more than 23 hours just to reach it. One way. We had the chance to send a third probe. We had the technology. We had the science. We even had the perfect window. We chose not to. Today we find out why, who made that call and what we lost. And stay with us because what scientists are quietly planning next will change how we see alien worlds forever. If you enjoy the journey, a like and subscribe keeps us going. Now, let's go. The most important space mission in human history started as a homework assignment nobody cared about. It was the summer of 1964. Gary Flandro was 27 years old, a graduate student at Caltech, working part-time at the Jet Propulsion Laboratory in Pasadena, California. He had been handed a routine task. Calculate low-energy flight paths to the outer planets. Standard stuff. The kind of work you give someone to keep them busy between bigger projects. Flandro sat down with his charts and his pencil and started mapping trajectories. He was looking at where Jupiter, Saturn, Uranus and Neptune would be positioned over the coming years. And somewhere in that work, something caught his eye. The planets were moving toward each other. Not physically. Planets don't crash together. But from the perspective of a spacecraft launching from Earth, they were converging into a rare geometric lineup. A spacecraft sent at exactly the right moment could swing past Jupiter, use that planet's gravity like a slingshot and get hurled towards Saturn. Then Saturn could throw it toward Uranus, then Uranus toward Neptune. 4 planets, 1 trip. A journey that would normally take 40 years compressed into fewer than 12. Flandro ran the numbers again, then again. The window would open in the late 1970s, and here is the part that should stop you cold. That alignment only happens once every 176 years. The last time the planets had lined up anything like this, Thomas Jefferson was sitting in the White House. Steam engines were new technology. The United States had fewer than 20 states, and in 1964 nobody at NASA had noticed. Flandro published his findings 2 years later in a scientific journal. The paper had a long title that most people would never read. But the idea inside it was simple enough to change everything. You could visit all 4 outer planets in a single mission, but only if you launched within a very specific window. Miss it, and you wait until the next century. Word spread through the agency fast. Engineers who had been sketching out ideas for expensive, slow missions to individual planets suddenly saw a completely different possibility. You wouldn't need separate missions for each planet. One well-timed launch could do the work of 4. NASA leadership got excited in a way the agency hadn't felt since the moon race. A briefing was prepared for the White House. According to people in the room, NASA's chief administrator looked at President Nixon and said that the last time the planets aligned this way, Jefferson was at that desk and he missed the chance. The implication was clear. History was watching. The window was real, and it would close. What nobody in that room could predict was how many forces would line up against this mission before a single spacecraft ever left the ground. Political pressure, budget wars, competing programs. One decision made in a single month that would echo for 50 years. Flandro's pencil and paper calculation set off a chain of events that sent 2 probes to the edge of the known universe. But the third probe he made possible, that's a different story. And it starts with a dream so big that the moment it was written down, the government started looking for ways to kill it. Picture 4 bowling balls rolling across a massive table, each one moving at a different speed, each one circling the same center point. Most of the time they're spread out, scattered. Useless to anyone trying to bounce something between them, but every once in a great while they drift into a curved line, close enough together that a marble flicked past the first one would curve toward the second, then the third, then the fourth. That is the outer solar system. And that alignment is what Gary Flandro found. Jupiter, Saturn, Uranus, and Neptune all orbit our star, but at wildly different speeds. Jupiter takes about 12 years to complete one lap. Saturn takes nearly 30. Uranus takes 84. Neptune takes 165. Because each one moves at its own pace, getting all four into a useful geometric arrangement is extraordinarily rare. The reason the alignment matters so much is gravity assist. When a spacecraft swings close to a massive planet, the planet's gravity grabs it, whips it around and throws it forward. The spacecraft gains speed without burning a single drop of fuel. It's one of the most elegant tricks in all of physics, and it works best when the next planet is already sitting in roughly the right direction. Without the alignment, you'd have to aim for one planet, then wait years in deep space while the next one drifted into position, burning fuel the whole time. With the alignment, each planet acts like a relay racer passing a baton to the next. The spacecraft keeps accelerating across billions of miles. The 1977 window was exceptional. Jupiter, Saturn, Uranus, and Neptune were arrayed in a curve that engineers could actually fly through. A spacecraft launched at the right moment could reach Neptune in about 12 years. Launch at the wrong time, or aim wrong, and even with all the fuel in the world, the math stops working. Here is what makes this genuinely hard to sit with. The previous comparable alignment happened around the 1700s. The next one after 1977 won't come until somewhere around the 2150s. That's not a planning horizon. That's a different civilization. Scientists confirmed this window was real. Confirmed it was rare. Confirmed that a mission designed around it could reach places no spacecraft had ever gone, in a time frame humans could actually plan for and live to see the results of. The clock was already running in 1966 when Flandro published. The launch window for the ideal Grand Tour trajectory would open in August of 1977 and close within a few years. Every month of delay chipped away at the geometry. What nobody was saying out loud yet, but what every engineer in the room understood, was that this was a one-time shot. You couldn't come back next decade and try again. You couldn't wait for better technology or a bigger budget. The planets didn't care about any of that. They were moving. They were always moving. And the window was already closing. For a few years in the late 1960s, NASA had a plan so bold it barely seemed real. 4 spacecraft, all 4 outer planets, every world beyond the asteroid belt visited in a single coordinated mission called the Grand Tour. Scientists had spent years arguing for exactly this kind of program, and now, with Flandro's calculations proving it was physically possible, the agency finally had the geometry to back up the ambition. The design was not the stripped-down, no-frills hardware you might imagine. The Grand Tour spacecraft were going to use a platform called the Thermoelectric Outer Planet Spacecraft, a new generation of deep space hardware that was heavier, smarter, and more capable than anything JPL had built before. These were machines designed to survive decades in the cold and dark, to keep sending data back across billions of miles, to photograph and measure worlds no human eye had ever seen up close. The mission structure called for 2 pairs of launches. The first pair would visit Jupiter, then Saturn, then swing out toward Pluto. The second pair would visit Jupiter, then Uranus, then Neptune. Together, all 4 spacecraft would build a complete scientific picture of the outer solar system. Every giant planet, every major moon system, every magnetic field, every atmosphere. The estimated cost landed somewhere between $750 million and $1 billion. In the early 1970s, that was real money. The kind of number that made budget officers nervous and gave politicians something to circle in red ink. But here's what that number actually bought. It bought the only chance, in any of our lifetimes, to send scientific instruments to every outer planet. Uranus had never been visited. Neptune had never been visited. These weren't abstract dots on a chart. They were entire worlds, as large as a small country is wide, wrapped in gases and storms and magnetic fields that science could only guess at from a distance of billions of miles. The scientific case was overwhelming. The engineering was ready, the trajectory was confirmed. A generation of planetary scientists had built their careers around the dream of exploring the outer solar system, and the Grand Tour was the moment it was all supposed to come together. Inside JPL, people were drawing spacecraft layouts, running simulations, calculating communication delays. The excitement was real, and it was earned. This wasn't speculation. The math worked. And for a brief moment, it looked like it was actually going to happen. Then the money talk started. Congressional staff began reviewing the proposal. The Office of Management and Budget weighed it against everything else the government wanted to spend money on. Vietnam was still burning through billions of dollars a year. Domestic programs were expanding. Apollo had cost an extraordinary amount, and the public was starting to ask whether the returns justified the price. The Grand Tour sat on the table while forces completely outside the control of any scientist or engineer began circling it. What happened next had nothing to do with physics and everything to do with politics. And one decision, made in a single month, didn't just shrink the Grand Tour, it erased it. $1 billion is easy to say, harder to approve. In the early 1970s, NASA was already in financial trouble. The moon program had cost an enormous amount, and with astronauts walking on the lunar surface becoming almost routine, public enthusiasm was cooling fast. Congress was in no mood to write another enormous check for another enormous space program. The Grand Tour arrived at exactly the wrong moment. The proposal crossed the desks of budget analysts who were looking at a NASA request that included the Grand Tour, the Viking Mars landers, early studies for a space telescope, and a dozen other programs all competing for the same shrinking pile of money. The Office of Management and Budget, which had the power to shape what NASA could even ask Congress for, looked at the Grand Tour's price and flagged it immediately. $1 billion for robots flying to distant planets was a very hard sell to a government focused on the cost of everything else. The Vietnam War was draining the Treasury. President Nixon was trying to restructure domestic spending. Every federal agency was being told to cut back. NASA's Planetary Science Division tried to defend the Grand Tour. Scientists testified about the rare alignment, the one-time opportunity, the irreplaceable science. They used clear language. They made the case carefully. The 176-year window argument was front and center. Congress listened. And then Congress started asking what could be cut. The thermoelectric outer planet spacecraft platform was expensive. The 4-spacecraft structure was expensive. The mission to Pluto required a trajectory that added time and cost. Budget negotiators began suggesting a smaller version. Fewer spacecraft, fewer planets, simpler hardware. Inside JPL, engineers watched the Grand Tour get slowly dismantled in meeting rooms and budget hearings they weren't invited to. Every concession that made the program cheaper also made it less complete. Dropping the Pluto trajectory saved money but abandoned an entire world. Cutting from 4 spacecraft to 2 cut the science in half. By December of 1971, the Grand Tour program was officially cancelled. The reason recorded in the official documents was cost. $750 million to $1 billion was too much to spend on outer planet exploration. Here is the part that is genuinely hard to square. The entire cost of the cancelled Grand Tour, adjusted for today's prices, is less than what NASA's science division spends in a single year right now. The mission that would have sent 4 spacecraft to every outer planet was killed over a sum that would barely register in a modern federal budget. The scientists who had spent years building toward this moment watched the program disappear. Some of them kept fighting. They pushed for a scaled-down replacement, something smaller, cheaper, targeted at just 2 planets. They got it, eventually. But the thing they got was fundamentally different from what they had designed. And the 3rd spacecraft, the one that would have gone to Uranus and Neptune on the 2nd trajectory, was gone. Something even bigger was about to take its place, and it came from the White House. In January of 1972, President Nixon signed off on the Space Shuttle program. The same month the Grand Tour was dying, the shuttle was born. Both decisions came from the same budget environment. Both were shaped by the same political pressures, and together they locked in a course for American space exploration that would last for decades. The Space Shuttle was a reusable spacecraft designed to carry astronauts and cargo to low Earth orbit. Nixon's administration sold it as the future of affordable spaceflight. Launch a vehicle, bring it back, refurbish it, launch it again. The cost per mission would fall dramatically. Space would become almost routine. To get the program approved, NASA needed political allies. The most powerful ally available was the United States Air Force. The military had its own ideas about what a reusable spacecraft should be able to do, and those ideas shaped the shuttle's final design in ways that made it significantly more expensive to build. The payload bay got wider. The vehicle's ability to change its orbital path mid-flight got more demanding. The thermal protection system got more complex. Every one of those changes added cost, and all of that cost had to come from somewhere inside NASA's budget. The agency made a calculation. Human spaceflight, with its public excitement and political weight, was easier to fund than robotic science missions. The shuttle would anchor NASA's budget. Everything else would have to work around it. That meant the Grand Tour was gone. It meant the proposed thermoelectric outer planet spacecraft platforms were gone. It meant the 4-spacecraft vision of visiting every outer planet was gone, replaced by something smaller, cheaper, and politically survivable. Here is what makes this genuinely strange to think about. The Space Shuttle's first flight didn't happen until April of 1981. The program absorbed enormous development costs for nearly a decade before it ever left the ground. During those years, the money that might have funded additional outer planet missions was locked into shuttle development instead. The Voyagers launched in 1977 on completely separate hardware, the old Titan Centaur rocket, precisely because the shuttle wasn't ready yet. They made it out the door before the full weight of the shuttle's budget demands came down on the agency. A Voyager 3 never had that same luck. By the time anyone might have seriously argued for a third spacecraft, the shuttle program had consumed the financial oxygen in the room. Every dollar the agency had was already spoken for. The engineers at JPL understood this. They had watched the Grand Tour shrink and then disappear. They had accepted the 2-spacecraft mission that replaced it, and some of them decided to do something about the limitation in the only way they still could. They built a secret into the spacecraft, and that secret is why Voyager 2 ever reached Uranus and Neptune at all. The official mission was simple: 2 spacecraft, 2 planets, Jupiter and Saturn. That was the deal Congress approved. That was the program that got funded. The engineers at JPL built something else entirely. When the Mariner Jupiter-Saturn 1977 program replaced the Grand Tour, the spacecraft design was supposed to be a simpler, cheaper machine aimed at 2 targets. But the engineers who built Voyager 2 quietly designed it to survive conditions beyond Saturn. They installed hardware that could handle the colder temperatures and weaker signal strength of Uranus and Neptune. They built the onboard computer with enough flexibility to be reprogrammed from Earth years into the mission. They left capabilities in place that the official mission profile didn't ask for. Nobody announced this. Nobody submitted a budget request for a Uranus mission. They just built the spacecraft to be ready. This was a calculated risk. If the primary mission failed, none of the hidden capability would matter. If it succeeded, and if the science was good enough to justify continuing, they would have a spacecraft already in position, already designed to go further, and there would be a real argument for keeping it funded. It worked. Voyager 2 flew past Jupiter in July of 1979. The images were extraordinary. Public excitement built. Congress kept the money flowing. Saturn came in August of 1981. Again, stunning results. Again, more funding approved, and then JPL made its case. Voyager 2 was already heading in the right direction. Uranus was sitting roughly where it needed to be. The spacecraft could make it. The science would be historic. The cost of extending the mission was a fraction of building a new one. Congress said yes. In January of 1986, Voyager 2 became the first and only spacecraft in history to fly past Uranus. In August of 1989, it became the first and only spacecraft in history to fly past Neptune. Two worlds that had never been visited by anything humanity built. Two planets still studied today almost entirely on the basis of data collected during those flybys. The engineers' quiet gamble paid off completely. But here is the part that stays with you. That flexibility was built into Voyager 2. Voyager 3 was never built at all. There was no spacecraft sitting in a warehouse with hidden interstellar capability, waiting for a funding argument to unlock it. The backup plan that saved the Outer Planet program only worked because somebody had thought ahead far enough to build it. Nobody built that same insurance for the mission that should have come next. The planets were still moving, the window was still closing, and now there were only 2 spacecraft where there should have been 4. Imagine trying to throw a ball through a moving doorway. The door is open for a few seconds. If you throw too early, the ball hits the frame. Too late, same result. The throw has to happen in a specific narrow moment, or the whole attempt fails. Now imagine the doorway is moving through space, and your ball takes 12 years to arrive. That is the Outer Planet launch window. The alignment Gary Flandro discovered gave engineers a usable trajectory from roughly 1977 through the early 1980s. Within that range, the geometry shifted constantly. The best trajectories for reaching all 4 outer planets in sequence required launching within a very specific stretch of months, with the ideal window concentrated around the late summer of 1977. Voyager 2 launched on August 20th, 1977. Voyager 1 launched on September 5th. Both made it through the window, both were on valid trajectories for Jupiter and Saturn, and Voyager 2 was on a path that could eventually reach Uranus and Neptune. Every day after September of 1977, the window for a Grand Tour trajectory got worse. By the early 1980s, you could still launch toward Jupiter or Saturn, but the planetary lineup for swinging onward to Uranus and Neptune was gone. The geometry had shifted. Neptune had drifted past the optimal point. The relay of gravity assists no longer connected. Launching a third spacecraft in, say, 1980, would have meant sending it to Jupiter and Saturn at best, then watching it coast into deep space without being able to use those planets to reach further. The science would still have been valuable, but it wouldn't have been a grand tour. It would have been a repeat of what the first 2 spacecraft were already doing. By the time NASA had the budget conversations, the political will, or even the serious proposal for a third probe, the window that made the Grand Tour extraordinary had already closed. This is a 176-year problem. The next comparable outer planet alignment won't arrive until sometime around the 2150s. The scientists who would need to design that mission haven't been born yet. The engineers who would build it are decades away from starting school. There is no shortcut. The planets move on their own schedule. What this means for any future interstellar probe is something the next generation of scientists is actively working on. And the solution they've come up with doesn't rely on planetary alignment at all, but getting there requires understanding just how extraordinary the original launch actually was. Because what both probes did after leaving Earth, in the span of a single afternoon, was already unlike anything in history. What eventually got approved was a shadow of the original plan. The program that replaced the Grand Tour was called Mariner Jupiter-Saturn 1977. The name tells you exactly what Congress had approved. 2 planets, that's the mission. Jupiter and Saturn. Go there, collect data, come home. Except you can't come home from deep space, so come home just meant go silent eventually, somewhere beyond Saturn. The spacecraft were redesigned from the ground up. The heavy, expensive thermoelectric outer planet spacecraft platforms were scrapped. What replaced them was leaner, simpler and cheaper. Each probe weighed about 1,820 pounds at launch, roughly the weight of a small car. They carried cameras, magnetometers, plasma detectors, cosmic ray sensors, and radio science instruments, enough to do serious science at Jupiter and Saturn, enough to survive the journey. The official mission lifetime was 5 years. 5 years was long enough to reach Jupiter, execute the flyby, collect data, continue to Saturn, execute that flyby, collect more data, and then transmit everything back to Earth before the hardware started failing. That was the plan. That was what the engineers were supposed to design for. What they actually built, as the previous chapter showed, was something quietly more capable. But officially, on paper, in every budget document submitted to Congress and every press release NASA put out, this was a 5-year mission to 2 planets. The name changed 3 months before launch. Mariner Jupiter-Saturn became Voyager. The renaming was partly practical, partly symbolic. The spacecraft had evolved enough from the original Mariner design that using that name felt misleading. And Voyager carried something the old name didn't, a sense of going further than expected. It turned out to be accurate in ways nobody publicly admitted at the time. The 2 spacecraft were assembled, tested and prepared at JPL through 1976 and into 1977. Engineers ran simulations, navigators calculated trajectories, scientists argued about which instruments to prioritize and where to point the cameras during each planetary encounter. And in the summer of 1977, both probes were loaded onto Titan Centaur rockets at Cape Canaveral, Florida. The spacecraft that would travel further from Earth than any human-made object in history was sitting on launch pads, waiting. And here is something that almost nobody gets right when they tell this story. Voyager 2 launched first. On August 20th, 1977, Voyager 2 lifted off from Cape Canaveral. 16 days later, on September 5th, Voyager 1 launched from the same pad. Voyager 1 launched after Voyager 2. So how did Voyager 1 end up in front? The answer is trajectory. Both spacecraft were aimed at Jupiter, but along different paths. Voyager 1 took a faster, more direct route. Voyager 2 took a longer curved path designed to set it up for the Uranus and Neptune legs of the journey. The trade-off was that Voyager 2's route was slower at the start. Voyager 1 caught up and passed its partner in the void between Earth and Jupiter. By the time both spacecraft arrived at the giant planet, Voyager 1 was ahead, and it stayed ahead for the rest of the mission. The numbering came from the projected order of arrival at Jupiter, determined before launch. Engineers knew Voyager 1 would reach Jupiter first because of its trajectory, so it got the number 1. The fact that it launched second is one of those small ironies that makes the mission feel even more human. Both spacecraft carried identical instrument packages, cameras capable of capturing detail that no Earth-based telescope could match, magnetometers to measure planetary magnetic fields, instruments to analyze the charged particles streaming through space, equipment to study the structure of planetary atmospheres by watching how radio signals bent as the probe passed behind each planet. The journey to Jupiter took about 18 months for Voyager 1. The spacecraft crossed the asteroid belt without incident, which had been a genuine concern before Pioneer 10 proved it was survivable in 1973. Deep space turned out to be mostly empty, even in the zones that looked crowded on maps. By early 1979, Voyager 1 was approaching the largest planet in the solar system, a world so massive that every other planet in the solar system could fit inside it with room to spare. What it found there was beyond anything the scientists had modelled. Voyager 1 arrived at Jupiter in March of 1979, and within hours, everything scientists thought they understood about the outer solar system got more complicated. Jupiter was already known to be enormous, a diameter 11 times wider than Earth's. A storm called the Great Red Spot that had been visible from Earth for centuries. A faint ring system that some astronomers suspected existed. What the spacecraft revealed was that every single one of those known facts was just the surface of something much stranger. The Great Red Spot, seen through Voyager's cameras, was a living storm system. Edges rotating at hundreds of miles per hour, smaller storms spiralling around its outer edge like water draining in a drain. the internal structure was nothing like what models had predicted. The planet's atmosphere was churning and layered and violent in ways that suggested the math for understanding gas giant weather was going to need serious revision. The ring system turned out to be real, thin, dark, made mostly of fine dust particles. Nothing like Saturn's spectacular rings, but real and confirmed for the first time. Then came the moons. Jupiter has dozens of moons, but the four large ones, Io, Europa, Ganymede and Callisto, were the targets. What Voyager 1 found at Io stopped scientists cold. Active volcanoes, multiple eruptions happening simultaneously, captured in the images. Io was the most geologically active body in the solar system, a moon covered in sulfur vents and lava fields, heated from the inside by Jupiter's tidal gravity squeezing and releasing it over and over like a ball of putty. Nobody had predicted this. Models had suggested Io might be geologically quiet. The discovery was made by a scientist reviewing the data only days before closest approach, giving the team just enough time to repoint some instruments. Europa, meanwhile, showed something different, a surface covered in ice, fractured, cracked, with long, linear features that looked like something was moving underneath. Scientists began asking whether liquid water might exist below that frozen shell. That question is still one of the most important in planetary science today. Voyager 2 arrived at Jupiter 4 months later, adding more data, more images, more confirmation that this system was stranger and richer than anyone had built into their plans. And ahead of both spacecraft, Saturn was waiting. Saturn had been the most visually striking planet in the sky for as long as humans had pointed telescopes at it. Everyone knew about the rings. From Earth, they looked like a single flat disk, maybe 2 or 3 distinct bands if you had a good telescope and steady air. Clean, simple, geometric. Voyager 1 reached Saturn in November of 1980 and sent back images that made the textbooks obsolete overnight. The rings were not a few flat bands. They were thousands of individual ringlets, packed together so tightly that from a distance they blurred into the illusion of solid structure. Thousands of separate lanes of ice and rock, each one following its own slightly different orbit, maintained by a combination of Saturn's gravity and the gravitational influence of small moons embedded within the ring system itself. Some of those moons were brand new discoveries. Shepherd moons, scientists called them, tiny bodies that used their gravity to herd ring particles into sharp-edged lanes. Their existence explained something that had puzzled astronomers for decades: why some ring edges were so crisp and clean instead of gradually diffusing outward. The rings also had waves in them, spiral density waves, created by the gravitational resonance of larger moons further out. The ring system was alive with motion and structure at scales that no ground-based telescope could ever have resolved. Voyager 1 also flew past Titan, Saturn's largest moon. Titan had been known to have an atmosphere, which was already unusual for a moon. What the spacecraft found was an atmosphere thicker than Earth's, made mostly of nitrogen, with a smoggy orange haze so dense that the cameras could see almost nothing of the surface underneath. Scientists had to wait for the Cassini mission, launched in 1997, to get a proper look at what hid beneath that haze. Voyager 1's path through the Saturn system was designed to get close to Titan. That choice had a consequence. The gravity assist from Saturn sent Voyager 1 upward, out of the plane of the solar system, on a trajectory that could never reach Uranus or Neptune. Voyager 1 was done with planets. Voyager 2 had taken a different path through the Saturn system, one that preserved its ability to continue outward. The two spacecraft were about to go very different places. After Saturn, Voyager 1 was done with planets. The close approach to Titan that made its Saturn encounter so scientifically valuable also determined where the spacecraft would go afterward. The gravitational curve of that flyby pushed Voyager 1 up and out of the flat plane where all the planets orbit. Uranus and Neptune were still sitting roughly in that plane, billions of miles further out. Voyager 1 would never reach them. It was heading in a completely different direction. For some people at JPL, this was a difficult thing to accept. The spacecraft was still healthy, its instruments still worked, it had film left in the cameras, so to speak, but the trajectory was physics, and physics doesn't negotiate. What Voyager 1 had instead was speed. Its path through the Jupiter and Saturn flybys had given it more velocity than Voyager 2, and that velocity was carrying it straight toward the boundary of the solar system, faster than any human-made object had ever moved. Scientists knew they had years of deep space travel ahead. The spacecraft would keep transmitting. Its instruments would keep measuring the thin soup of particles and magnetic fields that filled the space between the planets. There was still science to do, but there was one thing left first. In February of 1990, mission controllers made a decision that had nothing to do with science and everything to do with perspective. Voyager 1 was about to shut off its cameras permanently. The cameras weren't needed anymore. There were no more targets. The distance from Earth was so vast that pointing the cameras at anything useful had become nearly impossible. Before the cameras went off forever, Carl Sagan had been lobbying NASA for years to turn Voyager 1 around and take one last photograph. Not of a planet, not of a moon, of the entire solar system from the outside. What came back changed how a generation of people thought about where they lived. While Voyager 1 climbed out of the solar system's plane and aimed for the stars, Voyager 2 kept going. It left Saturn in August of 1981 on a trajectory that the JPL engineers had quietly built into it years earlier. Officially, the mission was over. The original program had covered Jupiter and Saturn. From a budget standpoint, everything after this was an extension, funded year by year, justified by new science at each stop. Uranus was next, 5.5 years away. That waiting period between Saturn and Uranus is easy to skim past, but the reality of it is worth sitting with for a moment. Voyager 2 travelled for more than 5 years through complete darkness, through a region of space where the signal from Earth was already taking hours to arrive, where no human instrument had ever operated before, keeping itself pointed, keeping its instruments warm, keeping its transmitters running. And it arrived. In January of 1986, Voyager 2 reached Uranus. Uranus is strange in a way that sets it apart from every other planet in the solar system. Its rotational axis is tilted at roughly 98 degrees, which means the planet essentially rolls through its orbit on its side. One pole points almost directly at the star it orbits for half of its year. The other pole sits in darkness for the same stretch of time. A single Uranian season lasts more than 20 Earth years. What Voyager 2 found there was a cold, quiet, deeply weird world. The atmosphere was nearly featureless compared to Jupiter and Saturn. Smooth, pale blue-green with almost no visible storm activity. But underneath that calm exterior, the magnetic field was doing something that baffled scientists immediately. It was tilted 60 degrees away from the planet's rotational axis, which should not be possible if the field was generated by a rotating conducting core the way Earth's field is. 10 new moons were discovered during the flyby, 2 new rings, and a magnetosphere so oddly shaped that it twisted and corkscrewed as the planet rotated, wrapping around itself in a way that had never been seen before. Scientists had one shot at Uranus. Voyager 2 gave them everything it could in the hours of closest approach, and then it kept going. Neptune was waiting, 3.5 more years out. In August of 1989, Voyager 2 reached Neptune, 4 billion miles from Earth, so far that a radio signal travelling at the speed of light took 4 hours and 6 minutes to make the one-way trip. Mission controllers in Pasadena had to send commands, and then wait more than 8 hours before they could even know whether the spacecraft had received them. Neptune had been almost entirely a mystery before this flyby. From Earth, it was a faint blue dot. Astronomers knew its size, its mass, and the fact that it had at least 2 moons. Beyond that, the planet was a blank. Voyager 2 arrived and found a world far more dynamic than anyone expected. The atmosphere was active in ways that Uranus's was not. Enormous storm systems dominated the southern hemisphere. The largest one, a storm roughly the size of Earth, had been raging long enough that scientists named it the Great Dark Spot. Winds inside it reached over 1,000 miles per hour, the fastest winds measured anywhere in the solar system at that point. Neptune's largest moon, Triton, turned out to be one of the strangest objects in the solar system. It orbits Neptune backward, moving in the opposite direction from the planet's own rotation, which means it was almost certainly captured by Neptune's gravity, rather than forming alongside it. Triton's surface had active nitrogen geysers shooting dark material miles into the thin atmosphere. Its surface temperature was the coldest ever recorded in the solar system at that time. 6 new moons were discovered during the flyby. Neptune's ring system was confirmed and partially mapped. Voyager 2 sent back its last planetary images in late August of 1989, and then it aimed for the open dark between the stars. It was the final planetary encounter in the entire Voyager program. There would be no Voyager 3 to pick up where it left off. No follow-up mission aimed at these worlds, no spacecraft returning to Uranus or Neptune for decades. The scientific community had received an extraordinary gift from 2 machines that outlived their mission by decades, and now they would have to make it last. What came next was not more data. It was a photograph. Carl Sagan had been asking NASA for years. He wanted Voyager 1 to turn around, to point its cameras back toward the inner solar system, to take a portrait of the place it had come from. The engineering team resisted. Turning the spacecraft and pointing its cameras toward the star it had launched from was risky. The brightness could potentially damage the camera systems, and the images would be scientifically nearly useless. The distances were so vast that no planet would appear as anything more than a speck of light lost in the glare. That was exactly what Sagan wanted. In February of 1990, with Voyager 1 about 4 billion miles from Earth, mission controllers commanded the spacecraft to turn around. It took photographs of 6 planets: Venus, Earth, Jupiter, Saturn, Uranus, and Neptune. The entire inner and middle solar system captured from the outside for the first time. The image of Earth showed up as a pale blue dot, less than a single pixel wide, caught in a beam of scattered sunlight. Sagan wrote about that image in a way that has outlasted almost everything else written about the Voyager program. He described Earth as a mote of dust suspended in a sunbeam, a lonely speck in the great enveloping cosmic dark. He used the image to make an argument that had nothing to do with astrophysics. He was talking about perspective, about what it means to live on a tiny rock in a solar system that is itself tiny, in a galaxy that is itself one of billions. After those photographs were taken, the cameras were shut off permanently. Voyager 1 would never photograph anything again. The images were too power intensive, the science return too low at the distances being covered. Every watt of electricity was going to matter more and more in the years ahead. What was left was the journey itself. Billions of miles of dark, empty space between the probes and the edge of the solar system's protective bubble. Scientists had a name for that boundary, and what the Voyagers discovered when they crossed it turned out to be far stranger and more important than anyone had predicted. Before either spacecraft left Earth, someone had to decide what to put on them. NASA had sent Pioneer 10 and Pioneer 11 into deep space in 1972 and 1973, each carrying a small gold anodized aluminum plaque with a diagram of a human figure and a map showing where the spacecraft came from. Simple, logical, scientific. For Voyager, Carl Sagan and a small team decided to do something far more ambitious. Each spacecraft carries a 12-inch gold-plated copper disc. On that disc is encoded 115 images, sounds from Earth including ocean waves, thunder, birds, and a baby crying, greetings in 55 human languages, and music from 27 different cultures, including works by Beck and Chuck Berry. A stylus is attached to the record, along with pictographic instructions showing how to play it. The cover includes a diagram of a hydrogen atom, which any sufficiently advanced civilization would recognize as a universal reference point. It includes a pulsar map that shows the position of Earth relative to 14 known pulsars, giving whoever finds it a way to locate the record's origin point in space and time. The whole thing was designed, curated, and assembled in about 6 weeks. Here is the part worth sitting with. The record was placed on the spacecraft knowing that no human being will ever meet whatever finds it, if anything ever does. Voyager 1 is moving at about 38,000 miles per hour, which sounds fast until you realise the nearest star system is about 25 trillion miles away. The probe won't reach even the outskirts of that system for around 40,000 years. The record is a message in a bottle dropped into an ocean so large that the concept of finding it by accident is essentially meaningless. It's there anyway. Scientists have argued over whether the record was wise. Broadcasting Earth's location to the unknown, even passively, is something some researchers think deserves more thought. Others say the signals humanity has been broadcasting in radio waves for a century have already done far more than a copper record could. Both probes carry this disk. Both are now in interstellar space, and both are running out of time. For decades, both spacecraft travelled through the outer solar system, measuring the thinning stream of charged particles flowing outward from our star. Scientists had a name for that stream, the solar wind, and they had a name for the boundary where it finally ran out of energy and stopped, the heliopause. Nobody knew exactly where it was. Models predicted it sat somewhere between 100 and 150 astronomical units from the star at the centre of our system. 1 astronomical unit is the distance from Earth to that star, about 93 million miles. So the heliopause was somewhere between 9 billion and 14 billion miles out. Voyager 1 was approaching that zone in the mid-2000s. Scientists were watching the data carefully, looking for the signature that would tell them the spacecraft had crossed the boundary. The solar wind would weaken. The density of interstellar particles would rise. The magnetic field would shift. The signals started changing in 2012. On August 25, 2012, scientists confirmed it. Voyager 1 had crossed the heliopause and entered interstellar space. For the first time in history, a human-made object was operating outside the protective bubble of our home solar system. The data coming back was immediately surprising. The magnetic field direction at the boundary was not what the models had predicted. The density of interstellar plasma was higher than expected. The transition happened in stages rather than all at once, suggesting the heliopause is not a sharp wall but a complex layered boundary that shifts and breathes over time. Voyager 2 crossed the same boundary on November 5, 2018, about 6 years later, and at a different point on the heliosphere's surface. Those 2 crossing points gave scientists something they had never had before: 2 simultaneous datasets from interstellar space taken at different locations. The heliosphere is not perfectly round, it turns out. It's shaped by the pressure of interstellar material on one side and the outward push of the solar wind on the other, forming something more like a comet shape, with a blunt nose facing the direction of travel and a long tail trailing behind. Both probes are now in that environment, measuring magnetic fields, cosmic ray intensities, and plasma density in a region of space that no model had ever been validated against, and both probes are dying. Voyager 2's crossing was different, and that difference turned out to matter enormously. When Voyager 1 crossed the heliopause in 2012, scientists got their first direct measurements of interstellar space. The data was extraordinary, but a single data point from a single location on a single day can only tell you so much. You can measure what's there. You can't tell whether what's there is typical, unusual, or shaped by local conditions that exist only at that spot. Voyager 2 crossed the heliopause on November 5, 2018, at a different point on the heliosphere's outer boundary. That 6-year gap between crossings was not wasted time. Both spacecraft were transmitting continuously, building a record of conditions across an enormous stretch of space. What the 2 crossing points revealed was that the heliosphere is asymmetric. The boundary on Voyager 1 side of the solar system sat at roughly 122 astronomical units from the centre. On Voyager 2's side, the crossing happened at about 119 astronomical units. 3 astronomical units of difference, around 279 million miles, at a different angle, under slightly different conditions of the interstellar medium pressing inward. That asymmetry was confirmation of something scientists had long suspected but never been able to measure directly. The heliosphere is not a perfect bubble. It gets pushed and squeezed by interstellar material flowing past it, by pressure from clouds of gas and dust in the galaxy, by fluctuations in the magnetic field of interstellar space itself. Voyager 2 also carried one instrument. Voyager 1 had lost years earlier, a working plasma science instrument. That instrument measured the temperature and density of the plasma in the interstellar medium at the moment of crossing, giving scientists data they had no equivalent for from Voyager 1's crossing. The plasma outside the heliosphere turned out to be significantly hotter than models had assumed. 2 crossing points, 2 sets of direct measurements, 2 slightly different pictures of the same boundary, taken years apart. And here is what that tells us that should make you genuinely uncomfortable. 2 data points cannot map a 3-dimensional structure. To understand the full shape of the heliosphere, the direction it's being pushed, the thickness of its walls at different locations, you need at least a 3rd measurement from a 3rd direction. That 3rd measurement does not exist. No spacecraft is heading for a 3rd crossing point, and the 2 probes already in interstellar space are running out of power. The clock for getting that 3rd data point is ticking, and it has been ticking since 2018. Most people have never heard the word heliosphere. That's worth fixing because what it describes is arguably the most important structure in our corner of the galaxy for the long-term survival of life on Earth. The heliosphere is a magnetic bubble. It's generated by the constant outflow of charged particles streaming from our star in all directions. That outflow, the solar wind, pushes against the interstellar medium, the thin gas and magnetic field that fills the space between stars in our galaxy. Where those 2 forces balance, the heliosphere's outer boundary forms. Inside that bubble, the solar wind dominates. Cosmic rays from deep space, high-energy particles produced by exploding stars and other violent events across the galaxy, get deflected and slowed. Some still get through, but the heliosphere absorbs a significant fraction of what would otherwise be a constant bombardment. Earth sits deep inside this protective structure, roughly 93 million miles from the centre. By the time cosmic radiation from beyond the solar system reaches Earth, the heliosphere has already done significant work filtering it. Remove the heliosphere, and cosmic ray exposure at Earth's surface increases substantially. Over geological time, that kind of elevated radiation bombardment affects DNA, disrupts atmospheric chemistry, and poses serious challenges to complex life. Here is the part that scientists confirmed only recently, and that most people still don't know. The heliosphere has probably not always looked the way it does now. Research published in the last several years suggests that roughly 2 to 3 million years ago, the solar system passed through a particularly dense cloud of interstellar gas. When that happened, the pressure from outside may have compressed the heliosphere dramatically. Some models suggest it may have shrunk so much that Earth sat near or even outside its outer boundary for a period of time. 2 to 3 million years ago is roughly when multiple hominid species were alive on Earth. The connection between elevated cosmic ray exposure and the fossil record of that period is something researchers are actively investigating. No confirmed link has been established, but the question is serious enough that multiple teams are working on it. This is exactly the kind of question that a 3rd interstellar probe, crossing the heliopause in a different direction, and measuring the interstellar environment ahead of the solar system's path through the galaxy, could help answer. Understanding the shape and strength of the heliosphere means understanding the long-term habitability of Earth. And right now, humanity's entire direct knowledge of that structure comes from 2 aging spacecraft that were built to last 5 years. Every year, both Voyagers lose roughly 4 watts of electrical power. 4 watts sounds like nothing. It's less than a dim light bulb. But on a spacecraft more than 10 billion miles from the nearest power source, 4 watts is the difference between a working instrument and a dead one. The Voyagers are powered by radioisotope thermoelectric generators, devices that convert heat from decaying plutonium-238 into electricity. When the spacecraft launched in 1977, each generator produced about 470 watts, enough to run all the instruments simultaneously, keep the electronics warm in the extreme cold of deep space, and power the transmitters that sent data back to Earth. Decades of radioactive decay have reduced that output significantly. By the mid-2020s, each spacecraft was operating on roughly a third of its original electrical budget. Every system on the spacecraft draws power. The heaters that keep electronics from freezing in the minus 450 degree Fahrenheit environment of deep space draw power. The transmitters draw power, the computers draw power. When the total available power drops below what everything needs to run, mission engineers have to make choices. Shut something down to keep something else alive. And they have to make those choices knowing they can never be reversed. Once an instrument is powered off on a spacecraft that far from Earth, there is no repair crew coming, no second chance. The data that instrument would have collected is gone forever. The power problem has been building for decades, and the Voyager team has known it was coming. They planned the shutdown sequence carefully, prioritizing the instruments that return the most unique and irreplaceable science from interstellar space. Each instrument that goes dark is a permanent narrowing of what humanity knows about the space beyond our solar system, and the shutdowns have already started. The timeline of shutdowns reads like a slow goodbye. In October of 2024, Voyager 2's plasma science instrument was turned off. That instrument had been active since launch in 1977, nearly 47 years of continuous operation. It was the instrument that measured the temperature and density of charged particles in the interstellar medium, the one that gave scientists the plasma data that Voyager 1 couldn't provide after its own plasma instrument failed back in 1980. Its loss means humanity now has no direct plasma measurements being taken in interstellar space. On February 25th, 2025, Voyager 1's cosmic ray subsystem was shut down. That instrument had been measuring the energy and direction of cosmic rays hitting the spacecraft from outside the heliosphere, data directly relevant to understanding how much radiation protection the heliosphere actually provides. On March 24, 2025, Voyager 2's low-energy charged particle instrument went offline. On April 17, 2026, Voyager 1's own low-energy charged particle instrument followed. Each shutdown narrows what both spacecraft can observe. What remains on each probe is a magnetometer, measuring the magnetic field of interstellar space, and a plasma wave subsystem, detecting radio emissions and plasma oscillations. Scientists estimate those final instruments may survive into the early 2030s before the power levels drop too low even for them. After that, both spacecraft go silent. Forever. For the first time since 1977, humanity will have nothing operating beyond the heliosphere. No instruments, no measurements, no data from the environment that shapes the long-term condition of life on Earth. The gap that follows could last decades. It could last longer, depending on what gets funded, what gets built, and when a successor mission finally launches. And when you understand what these probes are actually running on, the fact that they lasted this long feels almost impossible. When Voyager 1 launched, its onboard computer had about 69 kilobytes of memory. Take a single low-resolution photo on your phone, the kind you'd barely bother saving because the quality is too low to be worth keeping. That image file is likely larger than the total memory available to the computer, controlling the most distant human-made object in history. The software running on that computer was written in assembly language, the most basic form of computer code, close to the raw instructions a processor understands directly. Every command had to be efficient because there was almost nothing to spare. Engineers had to account for every byte. And yet that computer has been running science missions for nearly 50 years. Part of what makes this possible is the nature of the task. The spacecraft doesn't need to do complex calculations on the fly. It follows pre-programmed routines, executes commands sent from Earth, stores instrument data in a small onboard memory buffer, and transmits it back in a steady stream. The workload is repetitive and predictable, but the computer has also been reprogrammed from Earth multiple times over the decades. When engineers needed to add new fault protection routines, they uploaded new code from across billions of miles. When the power situation required changing how data was compressed before transmission, the software was updated remotely. When Voyager 1 went silent for months in 2023 due to a corrupted memory chip, engineers had to figure out how to patch a computer they couldn't touch, across a communication delay of more than 22 hours each way. They fixed it. The contrast between what these spacecraft run on and what we carry in our pockets is so extreme, it almost stops making sense. A modern smartphone has processing power millions of times greater than Voyager's computer, plus cameras, a cellular radio, a navigation chip, and enough memory to store every photograph both Voyagers ever took, thousands of times over. And yet the smartphone can't operate in deep space, can't survive the cold or the radiation, can't transmit data across 15 billion miles, and certainly hasn't been running continuously for nearly 5 decades. Engineering for survival in the most hostile environment imaginable turns out to require very different priorities than engineering for a device that fits in your pocket. Between 1977, when the Voyagers launched, and 1989, when Voyager 2 reached Neptune, NASA sent 0 new outer planet missions into space. 0. That 12-year gap was not accidental and not temporary. It reflected a fundamental shift in where NASA's money and attention had gone. The Space Shuttle program consumed the agency's development budget through the late 70s and into the 80s. Every major new initiative had to compete with shuttle funding, and most of them lost. Galileo, an orbiter mission designed to spend years studying Jupiter up close, had been in development since the late 1970s. It was supposed to launch in 1982. The shuttle's repeated delays pushed the launch to 1989. Then the Challenger disaster in January of 1986 grounded the entire shuttle fleet for more than 2 years, pushing Galileo's launch to October of 1989, the same month Voyager 2 was completing its Neptune flyby. Cassini, the Saturn orbiter that would eventually become one of the most productive planetary missions in history, wasn't launched until October of 1997, 20 years after the Voyagers. It took that long to survive the funding cycles, the budget cuts, and the political battles over whether large planetary science missions were worth their price. The Voyager mission itself had to fight for funding every year. The spacecraft were designed for 5 years. Every year after year 5 was a budget argument. Scientists had to justify keeping aging hardware alive against the argument that the money could go towards something new. The Planetary Society has documented this cycle in detail. Missions outlive their intended lives, continue producing science, and therefore continue consuming budget. That budget can't go toward designing successor missions. Successor missions get delayed. By the time they launch, the gap in direct measurement is already decades wide. This pattern repeated itself across planetary science throughout the 1980s and much of the 90s. The Voyagers kept producing, everything else kept getting pushed, and the opportunity that the 1977 launch window had briefly opened was quietly closing behind them, unmissed by any new hardware, unreplaced by any new mission aimed at the outer solar system or beyond. People ask this question all the time. We have better rockets now, better computers, better instruments. Why not just build a Voyager 3 and send it? The answer starts with the planets. The gravity assist chain that made the original Voyager trajectories possible required Jupiter, Saturn, Uranus and Neptune to be positioned in a specific curved arrangement. A spacecraft swinging past Jupiter gained enough speed and the right direction to reach Saturn. Saturn threw it toward Uranus, Uranus toward Neptune, Each planet added velocity through gravitational slingshot, cutting decades off the travel time. That arrangement no longer exists. The planets have moved. They will not return to a comparable configuration for roughly 150 to 176 years from now, placing the next useful Grand Tour window somewhere in the 2100s. A spacecraft launched today toward the outer solar system could still get a gravity assist from Jupiter. Jupiter is always out there, but Jupiter alone sends a spacecraft in roughly the right direction without the relay chain of the other planets. Without Saturn, Uranus and Neptune lined up as additional slingshots, reaching the distances the Voyagers have covered takes far longer. Voyager 1 is travelling at about 38,000 miles per hour, a speed achieved largely through that chain of assists. A mission launched today with only a Jupiter assist would exit the heliosphere in decades rather than 35 years, but would reach the distances Voyager 1 has covered significantly later. The deeper problem is propulsion. Chemical rockets, the same basic technology used to launch the Voyagers, have been refined over decades but remain fundamentally limited in how much velocity they can provide. To reach interstellar distances in a human planning horizon, without relying on planetary alignments, something different is needed. Scientists have been thinking hard about what that something different could be. Nuclear electric propulsion, solar sails, nuclear thermal engines, a close flyby of the star at the centre of our system to gain a gravity boost at the point of maximum speed. None of these are ready to fly today, but some of them are closer than most people realise, and the people working on them are running against a deadline that has nothing to do with orbital mechanics. When New Horizons launched in January of 2006, it was the fastest spacecraft ever sent into space at the time of launch. It crossed the orbit of the Moon in about 9 hours. Pioneer 10 took 11 hours to cover the same distance. New Horizons reached Pluto in July of 2015, sending back the first clear images of that world and its moons. The images were stunning, the science extraordinary, a geologically active surface, mountain ranges made of water ice, a vast nitrogen ice plain covering much of the southern hemisphere. After Pluto, New Horizons kept going. It flew past a distant icy object called Arakoth in January of 2019, and then continued outward on its current trajectory. By the mid-2020s, the spacecraft was more than 5 billion miles from Earth and heading into the outer solar system on what will eventually become an interstellar trajectory. So why isn't New Horizons a Voyager successor for interstellar science? 3 reasons. First, direction. The heliosphere has a nose, the side facing the direction the solar system is moving through the galaxy, and a tail pointing the other way. The most scientifically important crossing point is the nose, where the heliosphere is compressed by interstellar material flowing against it. New Horizons is heading in a direction that is neither the nose nor the tail. It will cross the heliopause somewhere on the flank. That's a less valuable location for understanding the heliosphere's structure. Second, instruments. New Horizons was built to study the Pluto system. Its instruments were selected and optimized for that target. It carries no magnetometer capable of measuring interstellar magnetic fields, which is one of the most critical measurements available in interstellar space. Without that instrument, it can't replicate what the Voyagers do. Third, power. New Horizons runs on the same type of plutonium power source as the Voyagers, and it will face the same power drain problem as it ages. Its instruments will start shutting down well before it reaches the heliopause. New Horizons is a remarkable spacecraft doing remarkable science. It is not a replacement for Voyager in any meaningful sense for interstellar research. The gap is still there, and it keeps getting wider. Both Voyagers will go silent sometime in the early 2030s. When that happens, humanity will have no instruments operating beyond the heliosphere. No measurements of the interstellar magnetic field, no plasma readings from outside the bubble, no cosmic ray data from the undiluted interstellar environment. That gap matters for reasons that go well beyond pure curiosity. The heliosphere's shape and strength directly affect how much galactic cosmic radiation reaches the inner solar system. Scientists trying to model this relationship need continuous data from both inside and outside the boundary. Gaps in that data are not just inconvenient, they are permanent. You cannot go back and measure what the interstellar environment was doing in 2035 if no instrument was there in 2035. The two Voyager crossing points have already told scientists that the heliosphere is asymmetric, and that its boundary conditions change over time. But two crossing points at two locations, separated by 6 years, and a change in the star's activity cycle, cannot build a three-dimensional picture of a structure tens of billions of miles across. A research paper published in recent years identified another layer to this problem. The solar system may currently be moving through a transition zone between two interstellar cloud systems. The properties of the interstellar medium immediately outside the heliosphere may be changing on timescales of thousands to tens of thousands of years. The two Voyagers caught a snapshot of that environment at a specific moment. What it looked like before, and what it will look like as the solar system moves deeper into the transition zone, requires sustained measurement over time. Without a successor mission in interstellar space, that record breaks. A science gap of this kind, once it opens, compounds. Models drift from reality. Assumptions harden into unchecked facts. The scientific community loses the ability to validate its predictions against actual data, and the cost of correcting that drift decades later is enormous. The urgency is real, and some scientists have spent years designing a mission that could close this gap before it opens. Here is something that sounds like it belongs in a movie script. Our star's own gravity can act as a telescope. Any massive object bends light as it passes by, a prediction of general relativity that has been confirmed repeatedly since Einstein first described it. The star at the centre of our system is massive enough to bend light from distant sources significantly, focusing it to a point on the far side of the star like an enormous curved lens with our star at its centre. At a specific distance on the far side of that star, the focused light converges into a focal region. Any telescope positioned in that focal region, pointed back at the star with a distant target behind it, would be looking through the most powerful natural telescope in our neighbourhood of the galaxy. The estimated distance to that focal region is 550 astronomical units from the star. 1 astronomical unit is about 93 million miles. 550 of them is roughly 51 billion miles. Voyager 1 has travelled for nearly 50 years and covered about 160 astronomical units. 550 is more than 3 times further. A telescope at that location, using the star's gravitational lens to focus light from a nearby star system, could theoretically resolve surface features on a planet orbiting that star. Continent-scale features, ocean signatures, possibly atmospheric chemistry, possibly biosignatures, chemical fingerprints of biological activity. A peer-reviewed mission concept published in 2022 describes exactly this. A spacecraft carrying an appropriate telescope positioned at the focal region, pointed at a target star system while the star we orbit acts as the optical element between them. The estimated surface resolution for a nearby exoplanet is roughly 15 miles per pixel. For context, 15 miles per pixel would let you see the rough outline of a continent. It would show you whether a planet has a blue ocean or a brown desert. It might show you cloud patterns. Scientists have never seen another planet's surface with their own eyes. With a gravitational lens they could. But getting a spacecraft to 550 astronomical units is a problem that has no easy answer. 550 astronomical units is not a distance that fits easily into any comparison we use for space. The Moon is about 250,000 miles away. The average distance from Earth to the star it orbits is about 93 million miles. Neptune, the farthest planet, sits about 2,800,000,000 miles from that star at its most distant. 550 astronomical units is 51 billion miles. more than 3 times the distance Voyager 1 has covered in nearly 50 years of continuous flight. To put it another way, if Voyager 1 had been aimed at the gravitational lens focal point instead of its actual trajectory, it would need another 100 years of travel to get there, even at its current speed of about 38,000 miles per hour. That's the fundamental problem. The science at the gravitational lens is extraordinary. The distance makes it nearly inaccessible with current technology. Scientists working on this problem have proposed a different approach. Instead of simply launching a spacecraft on a conventional trajectory, they propose using a close flyby of our star as a velocity boost. A spacecraft with a high-performance upper stage would first swing into a tight orbit around the star, getting closer than any spacecraft has gone before, and use the star's own gravitational pull at maximum speed to gain tremendous velocity. Combined with solar sails that deploy at close range to catch the intense radiation pressure so close to the star, the spacecraft could potentially reach speeds several times greater than anything currently in interstellar space. At those speeds, reaching the gravitational lens focal point might take 25 to 30 years rather than a century. A small demonstration spacecraft called Sundiver, a CubeSat with fan-shaped solar sails, has been in development at the Jet Propulsion Laboratory, with a potential launch around 2027. Full mission could potentially fly in the early 2030s, though the technology still requires more work before anyone is committing to a launch date. The scientific prize waiting at the end of that journey is unlike anything humanity has ever attempted to observe, but it sits alongside a different mission, one aimed not at alien worlds but at understanding our own backyard, which has been in serious planning for years and still has no money to fly. In 2018, NASA commissioned a formal mission study from the Johns Hopkins Applied Physics Laboratory. The goal was straightforward: design a spacecraft that could reach interstellar space faster than the Voyagers, carry modern instruments capable of answering the questions the Voyagers raised but couldn't fully resolve, and build something that could survive long enough to take sustained measurements far beyond the heliosphere. 4 years of detailed engineering study followed. Hundreds of scientists and engineers contributed. The mission concept that emerged is called the Interstellar Probe. The baseline design calls for a launch between 2036 and 2041, on a rocket powerful enough to send it directly outward on a hyperbolic trajectory. It would make a single Jupiter gravity assist, then fly straight for interstellar space. With a high-performance upper stage, it could travel at 5 to 10 astronomical units per year. Voyager 1 averages about 3.5. At those speeds, the Interstellar Probe would exit the heliosphere in 12 to 16 years after launch, compared to the 35 years it took Voyager 1. It would carry modern magnetometers, plasma instruments, cosmic ray detectors, imaging systems, and heliospheric science packages that would produce data orders of magnitude richer than the Voyagers can still provide. The nominal mission length is 50 years. Ralph McNutt, one of the mission's lead architects at Johns Hopkins, said it plainly in 2021. If the spacecraft launches in 2036 and the nominal mission ends in 2086, he would be about 130 years old. He's not worried about it. These missions get handed off. That is a genuinely unusual thing to design for. A mission so long that the people building it plan for their own irrelevance as part of the engineering process. The instruments have to last. The ground teams have to be replenished across generations. The science goals have to be written broadly enough that scientists not yet born will find them meaningful. The study was completed and submitted to the Decadal survey in 2022. For the first time in the history of that survey process, something significant happened. The next outer planet alignment, comparable to the one Gary Flandro discovered, arrives somewhere around the 2150s. That is not a planning horizon. That is a different era of human civilization if there is one. The scientists alive today cannot design a mission around it. The engineers who would build it are not yet born. The political institutions that would fund it do not yet exist in any form that would recognize such a commitment. The Grand Tour window of 1977 was unique, not just because of its geometry, but because it coincided with a moment when spaceflight technology, had just matured enough to take advantage of it. Both conditions were required. The planets aligned, and the technology was ready. Waiting for the next alignment means waiting for both conditions to coincide again. There is no guarantee they will, so the scientists designing the next generation of deep space missions have moved away from alignment-dependent strategies entirely. The Interstellar probe concept from Johns Hopkins uses only Jupiter as a gravity assist, and Jupiter is available on a far more regular schedule. The solar sail approach for the gravitational lens mission uses our star's own energy and gravity as the propulsion system, available at any time. What both approaches require instead of planetary alignment is propulsion technology that doesn't yet exist at flight-ready status, but is closer than it has ever been. Nuclear electric propulsion, which uses a nuclear reactor to generate electricity that drives an ion engine, could provide continuous thrust over months and years, gradually building speed far beyond what a chemical rocket achieves in a brief burn. Several nations are actively developing this technology. Serious flight demonstrations are being discussed for the late 2020s and early 2030s. Nuclear thermal propulsion, which heats propellant directly with a reactor for a much higher exhaust velocity than chemical rockets, is being developed under programs at NASA and the Department of Defense. Solar sails, demonstrated at small scale by missions including Japan's Icaros spacecraft in 2010, and several CubeSat missions since, are being designed at larger scales. The tools exist in concept, some exist in early hardware. The question is whether they will be funded, built and launched before the science gap becomes permanent. In early 2026, NASA nearly lost a quarter of its science budget. The proposed federal budget put forward by the administration called for cuts across multiple agencies. For NASA's science division, the proposed reduction was severe enough that it would have forced cancellations of active missions and almost certainly ended any realistic planning for a new interstellar mission within the current decade. The planetary science community mobilized. The Planetary Society ran public campaigns. Scientists testified. Letters went to congressional offices. The argument was straightforward. These missions take decades to develop. Cutting the budget now doesn't just delay science, it erases it. The Voyagers won't wait for a budget recovery. The Senate rejected the proposed cuts. The final fiscal year 2026 NASA budget came in at $24.4 billion, roughly preserving the science division's funding at approximately the previous year's levels. That outcome was significantly better than what had been proposed. It kept active missions funded. It preserved the workforce that develops future missions. It maintained the basic infrastructure of deep space communication, the deep space network of giant radio antennas that still talks to both Voyagers every day. What it did not do was provide dedicated funding for a new interstellar mission. The Interstellar probe study was complete. The Decadal survey had recommended action. But a recommendation is not a funded program. A budget preserved at prior year levels is not a budget with room for a new flagship mission costing hundreds of millions or billions of dollars to develop. The gap between scientific consensus and funded action remained exactly where it had been. This is the structural problem that has defined deep space science for 50 years. The window that created the Voyager program was an act of nature, a rare geometric gift. The political and budget conditions that allowed it to be used barely were a near thing, and the conditions that have prevented any follow-up ever since have been consistent and durable. Science moves at the pace of funding moves at the pace of politics, and politics moves at its own pace entirely. Every 10 years, the planetary science community goes through a formal process called the Decadal survey. Scientists from across the field gather, argue, review proposals, weigh costs against expected science returns, and produce a ranked list of priorities for the coming decade. NASA and Congress use that list as a guide for what to fund. It's not binding, but it carries real weight. Missions that make the top of a Decadal survey list tend to get funded eventually. Missions that don't appear on it struggle to find support, For decades, no Decadal survey had ever recommended a mission explicitly aimed at interstellar space. The outer planets were priorities, Mars was a priority. The Moon, Jupiter's moons, Saturn's rings. Interstellar space sat at the edge of what the community treated as reachable science. In late 2024, that changed. The Planetary Science Decadal Survey for 2023 through 2032, released after years of review, included for the first time a recommendation that NASA develop a mission to interstellar space, specifically structured as a cross-divisional effort spanning planetary science, heliophysics, and astrophysics. All three divisions of NASA's science organization working together to send something beyond the heliosphere with modern instruments. The language in the recommendation acknowledged what the Voyager data had revealed about the heliosphere's complexity, the inadequacy of 2 data points for understanding a 3-dimensional structure, and the approaching silence of the only instruments humanity currently has in interstellar space. The recommendation also noted that the interstellar medium the solar system is currently moving through may be changing. The implications of that change for the heliosphere's protective capacity and for Earth's long-term radiation environment require direct measurement. For scientists who had spent years making the case for an interstellar probe, this was a significant moment. The community had spoken clearly and formally. The highest priority scientific processes had been documented. The case was as strong as the process allows it to be. A recommendation from the Decadal survey is the clearest signal science can send. What happens next depends on something the survey has no control over at all. A recommendation is not a rocket. That sentence describes the entire state of humanity's next mission to interstellar space as of mid-2026. The science case is made, the engineering study is done, the Decadal survey has spoken. The interstellar probe concept from Johns Hopkins is as complete and detailed as any unflown mission in planetary science. And there is no confirmed funding, no NASA program line, no launch date, no spacecraft being built in any clean room anywhere on Earth. The proposed launch window of 2036 to 2041 is close enough to feel real, far enough away to feel precarious. Flagship-class missions at this scale typically require 8 to 10 years of development after receiving authorization. Authorization requires funding. Funding requires sustained political support across multiple budget cycles and multiple administrations. The Voyager program itself nearly didn't make it. The Grand Tour was cancelled. The replacement program was stripped down. The engineers built hidden capability into the spacecraft without telling Congress. The mission was extended year by year. It survived on luck and stubbornness and the extraordinary longevity of hardware designed to last 5 years. The planets lined up in 1977. The technology was barely ready. The political moment was narrow, and 2 spacecraft slipped through the window before it closed. That window will not reopen in any of our lifetimes. The next chance to use gravity assists across all 4 outer planets won't come until the 2100s. What humanity has instead is propulsion technology getting closer to flight ready. A scientific community more unified in its priorities than it has been in decades. A decadal recommendation that puts interstellar science at the top of the list for the first time in history. And a ticking clock in the form of 2 spacecraft that are shutting down instrument by instrument, year by year, in the dark beyond the edge of the solar system. When both Voyagers finally go silent, there will be a moment. A day, some morning in the early 2030s, when the last signal arrives and the receiver at one of NASA's deep space antennas logs a final data packet from one of those spacecraft. And then, silence. The question that moment raises is not about the past. It's about what comes next. Gary Flandro found the window with a pencil in 1964. Engineers built a secret into a spacecraft and hoped nobody noticed. 2 probes launched in the summer of 1977 survived 10 times their expected lifetime and travelled further than any human-made object in history. Whether humanity sends something to follow them Whether the scientists who designed the interstellar probe live to see it launch, whether the Gravitational lens mission ever reaches 550 astronomical units and sends back the first image of another world's surface, none of that is decided by physics. All of it is decided by choices.